Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, thanks very much, and thanks to the organizers for inviting me out here. This is mainly work with Mike Jordan at Berkeley. Recently, we've roped in a couple other people. So my student Ka and Tamara Broderick, who's in statistics at Berkeley, has been involved in some of the results I'll talk about. Okay, so perhaps a more succinct title for the talk would be Generalizing K-means. So we've heard a couple of talks on K-means, and so everybody should be very familiar with K-means. What I'm going to talk about is looking at K-means from a statistical point of view, from in particular a Bayesian nonparametric point of view, and use that to come up with ways to generalize it and to make K-means a little bit more flexible. Okay, so I can overview this in a single slide. I can sort of give you the idea of what I'm going to talk about. So one way to think about K-means, again from a statistical sort of perspective, if you will, is you can take a mixture of Gaussians, which is a probabilistic model for clustering. You can look at, say, the EM algorithm for mixtures of Gaussians, and then you can, say, fix the covariances of your Gaussians and let them go to 0. And that's actually going to give you the K-means algorithm. So the EM algorithm becomes the K-means algorithm in the limit as the covariances of your Gaussians go to 0. I'll go through this in a little bit more detail later. But this idea, which we call small-variance asymptotics, leads very naturally to a question about what happens if you take the same idea and apply it to another mixture model, another clustering model. And so one of the things that I'll talk about today, which we presented at ICML this year, is what happens when we take this idea and apply it to a Dirichlet process mixture model, which is an infinite mixture model. So it's a mixture model where you don't fix the number of clusters. And if you take this sort of small variance asymptotics on that model, one question is, what do you get? Do you get anything interesting? And it's going to turn out you get a K-means-like algorithm, actually, but it's an algorithm that doesn't fix the number of clusters. So it's going to be K-means, but there's an extra step where you can actually start a new cluster. Okay? So we're going to get algorithms like this when we start looking at these sorts of asymptotic arguments on other mixture models. Okay? So this is, why should we kind of do this? I think K-means is a really great algorithm, and obviously a lot of people use it. It's also not the most flexible algorithm. You need to know the number of clusters. What if you want to do something with overlapping clusters, or what if you want to cluster multiple data sets simultaneously? It's not clear how to do that within a K-means type of framework. And some of that will become obvious when we do these asymptotics. Now, if you're a probabilist or you're Bayesian, this, I think, is interesting because you can obtain algorithms that scale a lot better than the algorithms that currently exist for Bayesian nonparametric mixtures, things like based on sampling, for instance. And there's going to be other connections, like connections to graph cuts and so forth, that become clear when we do this. Okay, so let's start with the basic result, which is the result's been around for a long time. It's a bit of folklore, I think you might say, which shows how to connect Gaussian mixtures and K-means. So we can start with a Gaussian mixture model. So I think everyone's probably familiar with this. You have some number of clusters K. You're assuming each cluster is generated according to a Gaussian distribution. So the parameters of the model are the means, the covariances, and then the mixing weights, these pi c's, of each Gaussian. So if you're going to do maximum likelihood estimation for this model, you have a data set. You try to maximize the likelihood, which is just the product over all your data points of P of x. And you try to find the parameters to maximize the likelihood. There's no closed form solution here. So typically you would resort to the EM algorithm. Right? The EM algorithm, sorry for the notation here, but the EM algorithm alternates between these two steps. You have the E step, which computes the probability that each point I is in each cluster C. So that's what I'm writing as gamma ZIC. Okay, so you have this. This is just essentially a posterior probability here, and then the M step uses those probabilities to then update the parameters, the means, the covariances, and the mixing weights of all of your clusters, and then you just iterate the process until convergence. Okay. So you can get from the EM algorithm to k-means very, very trivially. So again, as I said earlier, you take basically you're going to fix the covariances. You're going to say, I'm not going to estimate the covariances anymore. I'll just fix them. So I'll let each covariance be equal to sigma times the identity. Okay, and then if you look at the E step, probabilities, so the probability of a data point belonging to a cluster has the form that I have written over there. And now you ask what happens as sigma goes to 0, basically as the covariances shrink to 0. And what happens is that the probability that a point is assigned to a cluster goes down for all clusters except the one that's closest in terms of the squared Euclidean distance to the cluster center. So in the limit, what you get is the probability is 0 for all clusters except for the closest one. And that's nothing but the reassignment step for k-means. Okay. Now similarly, if you look at the M step where you're updating the parameters, the M step just ends up saying that you're going to update the sample mean of all the clusters. And so the E and M steps combined just become the k-means algorithm. And of course, the k-means algorithm monotonically minimizes the k-means objective function. Okay. So it's one perspective on k-means that you might not always see. You can also have a different perspective on the same thing, which is the EM perspective is an algorithmic perspective. You can also make a perspective on the model itself. So we can think of the mixture of Gaussians model as a particular instance of a linear-Gaussian latent feature model. And I'm presenting it in this way because we're going to look at other examples of linear-Gaussian latent feature models later. So in a linear-Gaussian latent feature model, you have the data. That's the xi's. That's what you observe. That's the shaded nodes. So you have your data. And each data point has a latent variable associated with it. That's the zi. And then you also have this matrix A. Okay, so in general, in a latent variable or a latent feature model, a linear-Gaussian latent feature model, you'd put a linear-Gaussian distribution on each of the xi's. So you say each xi comes from a Gaussian, and the mean of the Gaussian is A times zi, and the covariance we're just going to assume is sigma times the identity. Okay. The A's you can either treat as parameters or you can put a distribution on it. It won't really matter for what I'm going to talk about. If you put a distribution on it, you usually put a Gaussian distribution. And now, depending on how you select the z's, you get different kinds of models. So for instance, a mixture of Gaussians model would arise by putting a discrete distribution on theta, where theta are the mixing weights of your Gaussians. So if a discrete distribution just says, I have a vector of mixing weights, and so theta c is the cth mixing weight. So with probability theta c, zi will be a vector of length k, which is all zeros except for a 1 in the cth column. So each zi is an indicator vector, a cluster indicator vector. Okay. So if you do this, then you get this model, this generative model, where the A's are the means of the Gaussians, the Zi's are the cluster indicators, and so the generative model says first you figure out which cluster you're in by choosing from a discrete distribution based on the weights, and then you generate the data point from the mean corresponding to the cluster that you've chosen. That's what A times Zi gives you. Okay, so this is another way to think about mixtures of Gaussians, and you can do the asymptotics directly on the log likelihood of this mixture model. Okay, so you look at the joint log likelihood, which is just the probability of all your random variables here, the Z's, the X's, and the A's. You look at the log of that, and then you say what happens as sigma goes to 0. And then we have this notation for sort of asymptotically equivalent. As sigma goes to 0, the log likelihood becomes asymptotically equivalent to the negative k-means objective function. Okay. So you can say that the negative log likelihood asymptotically becomes the k-means objective function. This is a model kind of view of what's going on, right? So the question that I became interested in is what happens when we put other distributions on the Z's. Okay, so far we've looked at a discrete distribution, which is just the mixture of Gaussians model, but we could think about putting other latent variable distributions on the Z's, and some of this has actually been studied. So, for instance, if you put a continuous distribution, if you put a Gaussian distribution on your Z's, you get essentially what's known as probabilistic principal components analysis. You have to have another variable to account for the mean recentering. But otherwise, it's essentially what's known as probabilistic PCA. And then as sigma goes to 0, in this model, you would get standard PCA. You just get PCA that comes out in the asymptotics. Okay. So that's one example of a distribution. Let's look at some other clustering-based distributions. So there's something that some of you may have seen called the Polya Urn. Okay, so in the Polya Urn you have this urn, and it has k different colored balls in it. Okay, and theta here is a parameter, which we'll just assume is a non-negative integer. So you have theta balls of each color in the urn, and now you're going to sequentially, each data point is going to pick a ball from the urn, and the ball, the color will correspond to which cluster that the point is assigned to. So a data point goes and picks a ball from the urn, observes the color, assigns themselves to the corresponding cluster, and then puts the ball back, but then puts another ball back with the color that they chose. Okay, so you end up adding another ball to the urn every, each time a ball gets taken out of the urn. You're going to now repeat this for all n data points. Okay, so this actually will give you now a cluster indicator matrix, because each data point is going to have chosen a cluster, so you can write down this Z matrix that comes out of this process. And of course, if you were to repeat the process several times, you'll induce a distribution over these Z matrices. Okay. Now, the distribution that you get over the Z matrices is, of course, it's different from the discrete distribution that you get in a mixture of Gaussians model. In a mixture of Gaussians, you're simply choosing from a standard discrete distribution. Here you get a sort of a rich get richer phenomenon. Once a certain cluster gets chosen, once a certain color gets chosen, the subsequent data points are more likely to choose that point, or that color rather. Okay, so you can actually write down the probability distribution on the Z's here as conditioned on theta, the parameter. You have to do a little bit of combinatorics. This is called the Dirichlet-Multinomial Distribution. So if theta is an integer, then these are gamma functions. So they become factorials. But you can write down this distribution. Okay, and one thing you can observe about it is that it depends on k and theta and the sizes of the clusters. So despite the fact that it's a sequential process where your data points are sequentially picking balls from this urn, In fact, the distribution actually only depends on the size of the clusters. It's an exchangeable distribution. Okay, so now we can ask the question. Okay, we're going to take the linear-Gaussian latent feature model that we had, and the only thing that's going to be different is we're going to change the distribution on Z. We're going to put this Polya Urn distribution. And now we say, what happens when we do this small variance asymptotics as sigma goes to 0? Okay, and the answer is nothing actually interesting happens. If you simply have theta be some parameter that's independent of sigma, then nothing happens. But if you let theta vary with sigma in the right way, in particular if you have theta be equal to e to the minus lambda over 2 sigma, and then you do the asymptotics, what you get is kind of interesting. So you get a k-means objective function. Okay, and then you have another term which has a min operator and then a k and a k plus. K here is the number of clusters that you asked for. K plus is the number of non-empty clusters that you actually have. Okay, so if you were to say have an algorithm for this thing, K plus would be the number of non-empty clusters that emerge. So what does this say? It says that you want to minimize the k-means objective function, but you're going to pay a penalty for every cluster that you start up to some maximum of k. Okay. So it actually captures a little bit of the rich get richer kind of phenomenon that exists in the Polya Urn, because it says if you had two clusterings which have the same k-means cost, it's going to prefer the one that has fewer clusters, because of this second penalty term. Okay. All right, so that's an example of something that you would get when you do the asymptotics on a different distribution. Okay, it's not a Bayesian nonparametric distribution. It's a parametric distribution. So now you can go to the next step and say, what if you look at a nonparametric, a Bayesian nonparametric distribution on the clusters? And so we can look at what's called the Chinese restaurant process, which has become popular in the machine learning community. So here again, it's similar to the Polya Urn, where it's a sequential process where where each point is choosing a cluster. Okay. So here what we do is we imagine that there's customers entering a restaurant, and the restaurant has an infinite number of tables. Okay, and so the first customer comes in and sits at the first table. Okay, so they get assigned to cluster 1. And then each subsequent customer comes in and then sits at a table. They'll sit at a table that's occupied with probability proportional to how many people are seated at that table. And then with probability proportional to theta, we'll start a new table. Okay. So the second customer says, with probability proportional to 1, I'll sit at table 1. With probability proportional to theta, I'll start a new table. So maybe they start a new table. And then the third person says, okay, probability proportional to 1, sit at table 1. Probability proportional to 1, sit at table 2. Probability proportional to theta, sit at table 3. And so anyway, you can go through this process. And after n customers have come into the restaurant, you now have a clustering, okay? And it's a clustering where you have not actually specified the number of clusters that you want, right? It's random. So you in one particular run through the Chinese restaurant process, you might get 10 clusters, then you might get 15, etc. Okay. So again, this induces a distribution Z over cluster indicator matrices. And so now we can, again, go back to the Linear-Gaussian latent feature model. And we can say, well, if we put a Chinese restaurant process prior on the cluster indicator matrix, otherwise we leave everything the same. Okay, this is now a Bayesian nonparametric mixture model. We don't know, it's not fixing the number of clusters. Okay, and now we say what happens asymptotically. And in order to do this, in order to analyze this, you need to write down the probability distribution on Z. So you need to go back to Jim Pittman's Combinatorial Stochastic Processes textbook. And he talks about this exchangeable partition probability function, or the EPPF, which is actually nothing but the probability distribution on the Z's in the Chinese restaurant process. Okay, so just like with the Polya Urn, it depends only on the sizes of the clusters. So again, it's an exchangeable process. Even though it's sequential, it doesn't matter which order the customers enter the restaurant. The distribution is invariant to the ordering. So if you look at this and then you do the select theta as before, what you're going to get asymptotically as sigma goes to 0 is, again, a k-means-like problem. Except now you have a term here which is lambda times k. So you have a penalty for the number of clusters in the objective function. And lambda is the trade-off term that tells you how much penalty you're going to pay in the objective function for each cluster that gets formed. Okay? So again, in the objective itself, k is not fixed. It's going to be, it's determined by the, it's a part of the optimization. So lambda comes from theta. So if we go here, yeah. So we're doing the asymptotics, but we're making theta a function of sigma. So theta is actually going to 0, as is sigma. It's just that now we have lambda thrown in there. Okay. So that's a model, that's a likelihood view of what's going on here when you start doing asymptotics on these models. So when we wrote a paper for ICML this summer, we took a different perspective, which is the algorithmic perspective. So in the classical case, you have EM algorithm becomes k-means algorithm. Now you can ask the same thing about what happens to the algorithm for the Chinese restaurant process mixture. What happens to the algorithm in the limit? And so the algorithm that you use is based on Gibbs sampling. So I don't want to go through this in any great detail because there's a bit of background in terms of MCMC and so forth. The high level view is you're going to do this thing called Gibbs sampling, where suppose you have a probability distribution P of x, and you want to sample from it. Gibbs sampling says, well, I'm just going to repeat this process, this loop where I select each xi from the probability distribution of P of xi conditioned on all the other variables. And you just loop through all these xi's, and you do this, and you just repeat this, and eventually you're going to be sampling from P of x. The reason that that's important in the Chinese restaurant process mixture, or the Dirichlet process mixture, is you can't really do an EM algorithm for this nonparametric mixture model. What you want to do is you want to maximize, with respect to Z and A, the joint log likelihood, which is equivalent to maximizing the posterior, finding the map estimate. And so in order to get at the posterior, you need to do Gibbs sampling, or that's one way to do it. You need to sample from the posterior and then take the maximum. And you sample from the posterior using Gibbs sampling. And to do Gibbs sampling, then you need these two distributions. So basically, the key idea is for the algorithm, there's these two kinds of updates. There's a Gibbs move where you're updating the cluster indicator variables, and one where you're updating the means. And now you can say what happens on those particular steps of the algorithm as sigma goes to 0, and you get something sort of complicated. But in the end, as sigma goes to 0, it simplifies very nicely, and that's how you get the k-means-like algorithm. So if you look at the algorithmic updates on the cluster indicators, in the limit, what happens is very similar to k-means. So recall for k-means, you would compute the distance to every cluster mean, and then you would reassign the point to the closest cluster mean in terms of the squared Euclidean distance. Here what you're getting is you compute the distance to every cluster mean, and you reassign to the closest cluster mean unless the closest cluster mean has a distance greater than lambda. Okay? So what it says is, I'm going to do a k-means-like move, reassignment step, but if a data point is too far away from every cluster center, then I'm actually just going to start a new cluster with that one point as the centroid. Okay? That's what happens asymptotically in the Gibbs sampler. Okay? Now, the asymptotics of the update on the means just becomes the sample mean computation. So you end up with this algorithm, we call it DP means. Okay? It's just k-means, but it has this one extra step that says when I'm reassigning a point to clusters, and if the data point is past lambda in terms of distance to all the other clusters, then I'm going to start a new cluster. Okay? The other difference is we start with everybody in one cluster. Okay? So this is a k-means-like algorithm. It does not fix the number of clusters. The clusters sort of break off as you go throughout the algorithm.
So, if, like in the case of infinite data, can you say that this algorithm will converge to the maximum likelihood solution for your process?
In the case of infinite data, so you're asking about like the consistency of the algorithm. I don't know. I haven't thought about it. When you have infinite data, then you have an infinite number of clusters. Because as you get more clusters, or as you get more data, you tend to form more clusters. Anyway, that's a good question. I'm not actually sure. I know that there are certain results about consistency of k-means, whatever that means. And they might carry over to this case.
Just to clarify, your algorithm actually depends on the sequence in which you feed data.
Precisely, yeah. So k-means doesn't. K-means does not depend on the order of the data points. But this does because, you know, if you start a new cluster, it's going to affect all the subsequent points that you're. In fact, that's the only randomness in the algorithm because you're starting with everybody in one cluster. Of course, you could have a different initialization, but really the results actually depend on the ordering very, very much. So you can now you can sort of bring this all together, and you can show that the algorithm that I just described minimizes monotonically this Chinese restaurant process objective function, this weighted k-means plus lambda k objective function.
So did you show that it was lambda k before?
Yeah, so that came from this, when we looked at this model, which is the Dirichlet process mixture model. And we looked at asymptotically what happens. You get the k-means term plus the lambda k. That comes out of the asymptotics of the Chinese restaurant process.
Lambda k, it turned out to be lambda k because we chose theta in a particular way?
Yeah, because theta was chosen to decay in the right way.
Could you just remind me what theta was? E to the minus lambda?
Yeah, e to the minus lambda over 2 sigma. I mean, you can kind of see why that makes sense. You have a term here of theta to the k minus 1. So when you do the log likelihood, you're going to get k minus 1 log theta. And so you're going to get, if theta is minus log over 2 sigma, you're going to get something like minus lambda k over 2 sigma. And so that's just going to work out with the other terms that are 1 over 2 sigma from the k-means objective. Okay, so that's the algorithm, and that's the objective function. The algorithm monotonically minimizes this objective, so kind of it all sort of fits nicely. So in the last how much time do I have? Like 15 minutes. Yeah, in the last 15 minutes or so, I'll talk about some related models, including some of the stuff that we've done recently. So one of the benefits of this kind of analysis is that Now you can start looking at more complicated probabilistic models and then deriving sort of the k-means algorithm that comes out of them. So one of the things we looked at, one of the very first things we looked at is if you have this problem where you have multiple data sets. Okay, so here I have 3 data sets. I want to cluster each of them. And so I'm going to cluster them each into what I'll call local clusters. So each data set has its own set of local clusters. But I want that the means of these clusters are shared somehow across the data sets. Okay. So in a k-means framework, it's not clear how you would do this. In a probabilistic framework, it's very easy to do this because you take a bunch of mixture models and then you tie them all together with another variable. It's called like a hierarchical Bayesian model, for instance. So in the case of the Dirichlet process or the Chinese restaurant process, there's an analogous thing for multiple data sets. It's called the Chinese restaurant franchise, where you have multiple restaurants and then a global shared set of dishes. I won't go through the details. I can just tell you what you end up getting. You end up getting a k-means objective function here, or k-means-like objective function. It now is going to have 2 penalties. So now you're going to have, it turns out, a penalty for the total number of local clusters that get formed, and then a penalty for the number of global means. Okay, so you have these 2 different penalties now. So the number of local clusters, again, in this case you have 9 local clusters, and then you have 6 global means. So it says every time you start a new local cluster, you'll pay some penalty. Every time you start a global mean, you'll have a penalty. Depending on these penalties, how you set them, you can force sharing of these global means across the data sets. So you end up with a way to share means or share clusters across data sets, and then you can then derive the algorithm again from the corresponding Gibbs sampler, and you get this hard HDP algorithm that minimizes this monotonically. Okay. Another direction that we've looked at, which I won't discuss in any great detail, is exponential families. So I've been talking about this linear-Gaussian mixture, or this latent variable model. But in many cases, you wouldn't want to deal with Gaussian distributions. Maybe you have a mixture of multinomials or something. You have discrete data, for instance. You want to cluster it. And so you can ask if these results go through in the exponential family case, and you need to do the asymptotics there. And so it turns out that it does. It requires a little bit of effort when you're looking at the asymptotics of the algorithms, because you need to do these first-order Taylor approximations on marginal likelihoods. But it ends up working out very nicely. So there's this connection between exponential families and Bregman divergences. So each exponential family distribution has a corresponding Bregman divergence. And what you end up getting in the end is exactly what we had before, but where we replace the squared Euclidean distance with the corresponding Bregman divergence, which is what you would expect given previous results. Now, one of the nice applications of, once you start moving to exponential families, is you can start looking at things like topic modeling. So if you're familiar with latent Dirichlet allocation, it's a topic modeling approach. It's based on a hierarchical mixture of multinomials. You treat every document in a data set as a clustering problem, where you're clustering the words, but then you're sharing the word clusters across the corpus to form topics. So you can do this, now that we can do hierarchies and multinomials, we can do sort of a k-means topic model, hard topic modeling algorithm. And so we have some very preliminary results showing the kind of topics that you get on 2 different common data sets. These are sort of standard topic model data sets. And I think the real advantage of this approach is it's extremely fast. So you end up with, these are both, I think they have 2 million words or something in the corpus, and then the topic modeling, the k-means-like topic modeling algorithms converge in just a couple of minutes. So it's quite efficient. Another thing that we're looking at, which is very related, is what happens when we want to do overlapping clusters. Okay, so I've been talking about this case where the probability distributions on Z, so each Zi is just a binary vector with a single 1. Okay? Now, if we relax that and we say, well, Z could be an arbitrary binary matrix, that gives you an overlapping clustering model. Okay? So now you say, what are the distributions that you can put on the Z's to allow for this sort of multiple clustering situation? And then what are the corresponding asymptotic results here? So as it turns out, you can generalize all of the distributions I talked about before. So instead of a discrete distribution on the Z's, which is the basic thing, you'd put a Bernoulli distribution. So for every cluster, it's going to have some weighted coin, and if that coin comes up heads, you're going to assign yourself to that cluster. You're just going to do an independent Bernoulli trial for each of the clusters. Okay. That's going to give you a matrix that is binary, but is not a single assignment matrix. The generalization of the Dirichlet multinomial is called the beta Bernoulli. And then the generalization of the Chinese restaurant process is called the Indian buffet process. And you can do the asymptotics on all of these, and you get these sorts of k-means like multi-assignment things. So I'll just quickly talk about what happens in the Indian buffet process. That's probably the most interesting one. So, it's sort of fitting that I'm talking about this here. We haven't actually introduced it before. But you have this, this is the analogy or the sort of multi-assignment generalization of the Chinese restaurant process, if you will. Okay? So if you haven't seen the Indian buffet process, you have this Indian buffet, and it just has an infinite number of dishes. And so, and people are going along and just like sampling the dishes, right? And so the first guy comes in and samples some Poisson theta number of dishes. And then each subsequent customer will sample dishes based on how popular they are. So, and they're going to be done, it's going to be done independently. So you'll sample some dish with probability proportional to the fraction of the previous customers who have sampled that dish. And then at the end, you might sample some new dishes. Okay. So you can go through this process, right? This is a Bayesian nonparametric process. It gives you, again, it gives you a Z matrix because you end up, for every dish that you sample, you have a 1 in the Z matrix. But again, it's this infinite length matrix. The number of dishes grows unboundedly. And so now you can ask the question, what happens when you do the asymptotics on the Indian buffet process? Okay. Now, analogous to the Chinese restaurant process, we have to write down the probability distribution on Z. That's known. I won't go through it in detail, but it depends on various things. It's an exchangeable distribution, so the order of the customers doesn't matter. When you do the asymptotics here, you get this. You get a sort of, we call it like the Indian buffet means algorithm or something, or objective, and you get this objective that pops out. Okay. So you get so it looks a little bit like the k-means objective. So if Z were a single assignment matrix, it actually would be the k-means objective here. But since Z is allowed to have multiple assignments, you get something slightly different. You get A times Zi, and A as this form. Okay, so you end up with this objective. And then just like the Chinese restaurant process version, we have a penalty for the number of clusters that get formed. Okay? And again, you can derive an algorithm for doing this overlapping clustering Indian buffet objective. Okay, So I'm running out of time, so I'll just I'll briefly mention a couple other connections that arise here. One is you can look at connections to spectral clustering. So spectral clustering connections are known for k-means. So if you take the k-means objective function, you can write it as a particular trace maximization problem, and then you can relax it in a certain way such that the optimal solution can be computed via eigenvectors, and that gives you the spectral clustering relaxation for k-means. You can do the same thing for some of the models that I've talked about. So if you do it for this dp means objective, you get some sort of trace maximization problem that comes out, and again you relax the so y here is an orthogonal cluster indicator matrix. If you relax it to be just an arbitrary orthogonal matrix, then it says, well, the optimal solution is obtained by computing the eigenvectors of k, which is the Gram matrix of the data, corresponding to eigenvalues greater than lambda. So it's again a spectral solution, but it's got a slightly different rule in terms of how many eigenvectors you end up computing. You can also make connections to graph clustering, and this is something that I'm interested in, but I haven't actually done all that much with it yet. You can take advantage of existing connections between k-means and graph cuts. So, for instance, it's known that the sort of weighted k-means objective function is equivalent to certain graph cut problems, and you can use that to build algorithms for minimizing graph cuts. And so now you can actually do the same thing for these penalized clustering objective functions, and that leads to graph cut algorithms where you don't fix the number of clusters, or where you can have overlapping clusters and so forth in the graph. Okay, so just wrapping up. Basically, the focus has been on how to make a connection between Bayesian nonparametrics, which gives you these rich class of probability distributions, and sort of a more optimization-based view that you get in k-means. And so by doing these asymptotics, you obtain these non-probabilistic models that you get from the probabilistic models, from the rich probabilistic models. And I think that the benefits are clear. I think you end up, getting models where you don't have to fix the number of clusters, or where you can work with overlapping clusters or multiple data sets, et cetera. And it's interesting that what comes out of this is some pretty simple objective functions which regularize things like the number of clusters or the number of topics and so forth. It's also interesting that you get these, you can look at the asymptotics of the sampling algorithms, and that gives you certain algorithmic insights. So we've just started this work, so there's actually a lot to be done. There's lots of open questions here. For instance, can we analyze some of these algorithms in a way that, things like k-means have been analyzed? Can we come up with better algorithms? Can we find spectral relaxations for things like the HDP? What are the real killer applications of this stuff? So I think there's a lot of questions here, and a lot more to be done. Okay, thanks very much.
So maybe we have time for just one question before the yes.
Right. Yeah, so I conveniently ignored that issue in the talk. And so what we've been doing is very simple. We have heuristics for choosing lambda. If you know roughly how many clusters you want, I can give you a procedure that'll give you, an appropriate lambda for that. Yeah, I mean, in some sense, you're changing the question from k to lambda, and you still have a parameter here, and you still need to figure out how to select it, and that's an open problem. I mean, I think that's probably the biggest barrier to having these methods be really successful, is figuring out how to do that. And actually, some people have started looking at this. So after we presented this work at ICML. some people started looking at this, and there's I can point you to someone actually wrote a blog posting with their approach for selecting lambda. So anyway, so yeah, I think it's. Sorry, could you just repeat it? Yeah, I mean, basically, this is essentially like an AIC model selection problem, right? That's if you were to take k-means and do model selection via the AIC, you would get exactly this objective. So, so it's possible, you can look at what people have done in that context to pick lambda.